Electrochemistry Lab at the Separation and Conversion Technology Unit of Vito. We are a group of around 20 researchers working on different aspects of electrochemical conversions for various applications. In this lab, we work on both bioelectrochemical systems, which means we use living cells like bacteria or enzymes as catalyst, or classical electrocatalysts. So in the electrochemistry lab, we work with different reactors and setups, which can range from a small scale reactor, 10 centimeters square, up to a meter square reactor, which we work in the demonstration hall. One of the first type of cells that I would like to introduce now is a Beto Cell, as we call it, because it was designed and fabricated in-house by our colleagues at Vito. As you can see here, it contains several compartments, one for the gas and another for the liquid, but it is possible to combine several of these compartments to build even a small scale step at the lab. What you see here is an opening for the reference electrode, which is then connected inside by a thread. If you look at the compartment from inside, so this is a gas reactor, this is a liquid chamber, and as you can see, the material used can be ranging from PVDF to polypropylene and PMMA. The active surface area of the cell is 10 centimeters square, and we can fix our electrode like this here. So this is a gas diffusion electrode, which we will show you later. The second type of cell that we are currently using is called a microflow cell, and this microflow cell is currently being used for gaseous conversions, and mainly the gas that we are using for conversion is carbon dioxide, CO2, and we have several projects running on this, and we also want to integrate it with the renewable electricity and develop different bioelectrochemical as well as electrochemical processes for carbon dioxide conversion. So for lab scale experiments, this is an ideal cell because this is also very easy to assemble and fabricate. The active surface area of this cell is also 10 centimeters square. Again, we put a gas diffusion electrode here, we cover it with a current collector, and then we can close the cell. This is how the cell looks like, and it has two channels, one for the flow of the electrolyte, the liquid way, and one for the flow of the gas, which is the carbon dioxide in this case. Apart from the small scale setups that we use, such as this microflow cell with a surface area of 10 centimeters square, which we use to test different electrocatalysts or show proof of the concept of the reaction, in this case carbon dioxide electroreduction, we also try to upscale these systems up to a certain size. So in this case, what we show here is a syn cell where we have upscaled the similar cell up to a larger surface area of 400 centimeters square. This is a gas diffusion electrode, which I showed earlier, which we use to fit it in this cell. And this cell is an intermediate step before we built it up to a further larger demonstrations. This shows that the reactions that we are testing also work at upscaled sizes. So besides the Vito cell and the microflow cell, another type of setup that we currently use is an H cell. An H cell because it looks like English alphabet H, where we connect these glass bottles with a H bridge, where the membrane separates the anode from the cathode. In this case, this is a microbial electrosynthesis cell converting carbon dioxide to volatile fatty acids, and here the colored compartment that you see is where the bacteria is growing and attaching on the biofilm, whereas on the anode side we produce oxygen.
Here we have small scale electrochemical cells, here an H-type cell, and here a one compartment cell. We use these cells to investigate electrochemical reactions on a more fundamental level, to see how, for instance, the electrolyte influences the reaction, and also to screen different electrocatalysts. We work with small scale catalysts, for instance a wire or a small carbon electrode, and then we can also deposit the catalyst in nanoparticle format, and then we can investigate the activity and the selectivity. We can analyze our products by gas chromatography or liquid chromatography, and then we can say which electrocatalyst is the most selective, for instance.